In this video, we're going to extend the ideas about the formal proof or the formal definition of a limit to prove one of the limit laws that we were using last week, specifically the law of sums of limits. So in the last video, were showing that we had these formal definitions of what it means for the limit as x approaches a of f of x to exist, and what it means for the limit as x approaches a of a different function g of x to exist. We're going to prove that if these two limits exist, then we can add the limits together. If we add the two functions together, we can add the two limits together. That's what we're going to prove. We were using this fact to evaluate limits, but we want to prove that it's true. Within this proof, we're going to call on what's called the triangle inequality. Some of you may have learned this when you were in trigonometry. It seems kind of obvious. It's saying that whatever the length of the longest side of a triangle here, whatever that is, it has to be less than if I were to add side A and side B together. If we were to flatten A and B out like this, obviously that opposite side, A plus B, if it was equal, we would have a triangle that was, or if it was, sorry, greater than, we wouldn't be able to make a triangle. We wouldn't be able to close a triangle. So that seems like a kind of an obvious thing, but we'll just prove it to ourselves. We're using this absolute symbol to mean a distance or a length, the way we would in terms of vectors. So we're kind of transferring back to vector terminology. So we know that if we have a number x and we take its absolute value and then we square the absolute value, we're just going to end up with x squared. So let me give you an example. Let's say we start with a number 5 and we square the absolute value. Taking the absolute value of 5, we get positive 5. Squaring that, we get 25, right? Just x squared. What if that were negative 5? Well, when we take the absolute value first, we get 5 squared. We still end up with 25. So it's just saying that if you have an absolute value squared, it's going to be the same as just squaring the number on the inside. We also know that if we take the absolute value of a particular number, that's always going to be greater than or equal to that value x, because we're either taking the positive value if it exists, it's already positive, or we're making it positive if it started as a negative number. So we're going to use both of these facts. So we're going to select any two real numbers, a and b. And if we take the length of a and add it to the length of b, and then square that quantity, we square the first term, square the last term, and then we double up the two terms multiplied together. So that's this first part. Now, looking at this part, we're saying, okay, well, using this fact, we can say that the absolute value of a squared is going to be the same as this. And we can say that similarly, the absolute value of b squared is going to be the same as this. So we just made an exchange there. And then looking at the middle term here, we're saying that, okay, well, the absolute value of a, that's going to be greater than or equal to a. And the absolute value of b, that's going to be greater than or equal to b. So that's where this greater than or equal symbol is coming into, because we're saying that 2 absolute value a, absolute value b, that's going to be greater than or equal to this, just 2ab, dropping the absolute value symbols. So then taking this and just carrying it down, taking this inequality symbol, and then compressing this into its factored form, which is equal to this. So we have the absolute value of A plus the absolute value of B, quantity squared, is greater than or equal to, A plus B absolute value squared. Take the square root of both sides, and you're going to get this final thing that we have. So that's just our sort of mini proof of the triangle inequality, which we're going to use for our proof of the law of sums. All of these proofs start with us arbitrarily choosing some value epsilon that is greater than 0. And we have to find a delta greater than 0 such that anytime we pick a number that is in a neighborhood of A, we're going to get output values that are within a neighborhood of the limit. So just to remind you, what we were doing in the last video, we have some function. This is going to be the function f plus g. If I choose, this is L, this is the output value. Well, in this case, it's going to be L plus M. If I choose some neighborhood, this is going to be plus epsilon minus epsilon, right? Some neighborhood around that limit. This is A. We're having x approach A. This is A plus delta, and this is A minus delta, and we're trying to figure out what is this neighborhood around, sorry, I wanted a highlighter there. What is this neighborhood around A that'll lead to the desired neighborhood around L plus M, the limit? All right, so let's look at this. This is taking the two functions together. F has a limit at L and G has a limit at M. And so when we added them together, we combined their limits. But let's break this apart so that it's the F and the G are separated from each other. So what we're doing is we're just rearranging it. Instead of writing it this way, we're putting the F and the L together, and then we're putting the G and the M together. So we just rearranged the way that it was written. And then what we'll do is we'll use, at this point, we'll use the triangle inequality. So here is this, what we're given. And if we split this into its own inequality, I can see that here. And I split this, or sorry, into its own absolute value, this into its own absolute value. That's the triangle inequality there, right? I just split that into two separate absolute values. We know that we want to have this absolute value be less than epsilon. So what we're going to do, just to make it turn out the way we want, is we're going to have one of the F limit, we want that distance to be less than epsilon over 2, and then same for G. We'll have that, that limit be less than a distance of epsilon over 2. So that when we combine them together, we'll say, okay, overall, when we put those together, we're still less than epsilon. We're still within this neighborhood that we want to be. So this first part is just sort of our prediction of what we need to do to make the proof work out. We're just kind of analyzing behind the scenes what we think we need to do. So now we go to the proof. We're going to choose epsilon to be any number greater than 0, no matter how small it is. We know that the limit of f exists. And because of that, there is a delta. I'm calling it delta sub x, sorry, delta sub f, just to denote that it's the delta that's related to the function f. We know that there is some delta that exists so that if we choose x values around A that are within a particular neighborhood, it'll lead to output values that are going to be also within a particular neighborhood. This is restating the formal definition of the limit that we talked about in the last section. Similarly, because the limit of g exists, there's a delta sub g. So this is a different neighborhood around a related to the function g. So that if we choose any x values in that area, we'll be able to keep the y values within a certain neighborhood less than epsilon over 2 away from the limit. So like we did in the last example or in the last video, when we're trying to decide what we want delta to be, it has to be the smaller of the two. In this graph that I just drew, this kind of fake graph, I drew it in a way that the two values are not necessarily symmetric about a, and so we always go with the smaller one. So what we're saying in this next line is we're saying, okay, let's choose the minimum of the two deltas, the delta for f and the delta for g. Let's choose the smaller of them. So that then we know that when we choose x values that are really, really close to a, less than delta away from a, we know that the original limit that we're trying to analyze, which can be rewritten in this way, putting the f together with its limit and the g together with its limit, and then rewriting it using the triangle inequality. Each of these individual components, this one is less than epsilon over 2, this one is also less than epsilon over 2, and so together they combine to be less than epsilon. Again, we always need to have the formal proof that when we choose x within a particular neighborhood, the output values are going to be within this neighborhood of epsilon. All right, thanks for watching.